So the next example, example 6, is very similar to 5, except we're going to be integrating across two line segments. So again, we're going to have to break the integral up into two parts to cover curve 1 and curve 2. Again, remember that the equation for a line segment R is given by 1 minus t r naught plus t times r1. In this case, we can put it in a form that we talked about last year, since doing all of the math might not be time efficient. So we can say that rt is equal to some rate of change times t, which is r 1 minus r naught plus r naught. And r1 minus r naught is just going to be the difference between the points. So right now let's talk about C1. So we're going to have, in this case, r1 is 3. So we'll have 3 minus 2, and that'll give us 1. And then we'll have 4 minus 0, and that'll give us 4. And then we'll have 5 minus 0, and that'll give us 5, times t plus the original point, which is 2, 0, 0. And that'll give us all of our equations really quickly. So we can see that x is equal to t plus 2, y is equal to 4t plus 0, and z is equal to 5t plus 0. And again, t would go from 0 to 1. So those are our equations. We can figure out what dx, dy, and dt are, because that'll help us out. So dx is equal to dt, dy is equal to 4 dt, dz is equal to 5 dt, and now we just need to plug in for our integral. So the integral over curve 1 of the function f ds is equal to the integral from 0 to 1 of, in this case it was y dx, so we're going to have 4t dx is dt plus z dy, so z is 5t, dy was 4 dt, plus x dz, so x was t plus 2, dz was 5 dt. And when we simplify all of that, we're going to get the integral from 0 to 1 of 10 plus 29t dt, and integrating that, it's a nice easy polynomial, 24.5. So that's the value along the first curve. For C2, we can do the same thing. C2 is from 345 to 340. In this case, it's a vertical line, so we can sort of avoid a lot of the stuff. X isn't changing, so x is constant at 3, y is constant at 4, and the only thing that's changing is z, and we can see that z changes 5, so we'll have 5 minus 0, and the initial point for, or sorry, we're going from 0 to 5, so it would be 0 minus 5, and our initial point is 5. So we'll have z is changing by a value of negative 5t. Our initial point is 5. And so we're going to get that dx is equal to 0, dy is equal to 0, dz is equal to negative 5 dt. This makes sense because we're actually, we're doing a line integral across a curve, but that curve is actually just a one-dimensional line. So not a whole lot of what we're doing is very useful. So we're just going to get the integral from 0 to 1, and everything's going to go away except for the part that's in terms of z. So we're going to have x dz, so we'll have 3, and then dz is negative 5 dt. And integrating that, we're going to get negative 15. And so the total path would be the sum of the two, so we're going to have 24.5 minus 15. And so the value for the original integral that they were asking for is 9.5. Since the two integrals we did made up the complete curve.